Hi Bobcats. In this video, we're going to start looking at titrations. We're going to look at the technique in general and then at the specific case of a strong acid titrated with a strong base. Our objectives are to compare and contrast the titration curves of strong acids and strong bases and calculate the pH values or concentrations of relevant species at different areas along the titration curve. So we're going to actually divide the titration curve into 4 regions and take a little different approach depending on where we're at within those 4 regions. So let's take a quick review of titration. Hopefully you remember this from Gen Chem 1, but if not, and this is the first time you've seen it, there's no time like the present to learn it. The technique of titration is done with a tool called a burette. So the burette is the skinny calibrated glassware that you see up at the top of this image. And there's a valve on it that's called a stopcock, and you can use that stopcock to dispense titrant from the burette into your Erlenmeyer flask. The solution that's down in your Erlenmeyer flask is referred to as the analyte. It is the solution being analyzed. Get the pen going. So yeah, this solution that we have down below is referred to as the analyte. The solution that is up above in the burette is called the titrant, and the vocabulary that we use is you titrate the analyte with the titrant. So the thing that you're titrating is what's down there in the Erlenmeyer flask, and the thing you're titrating with is the thing that goes up there into the burette. Now you gradually add small amounts of the titrant into your flask, and what you will start to see is that right where the titrant hits the analyte, you get a local concentration of base, and that makes in this case it's base because the titrant is a base. So you get a local excess concentration in the base, and so you see pink color. That pink color is an acid-base indicator. This particular one is called phenolphthalein, and it is colorless in acid, and this hot pink color in base. At this point in the titration, if you stop adding the titrant and you swirl your Erlenmeyer flask, that pink color is just totally going to go away. So you keep adding the titrant until you have a pink color that persists and it's spread throughout your entire flask. Now, if you did this in the 1142 lab, you possibly could get a really bad grade because having this dark of a pink color for your phenolphthalein, it means that you have a significant excess of base that you have added, and it's impossible to tell whether you have 1 drop of base too much or 10 milliliters. Either case is going to look nice and dark like this. So we really want to strive for something that's a much lighter pink for your endpoint. Okay, so let's see, there are a couple of vocabulary words here. Yes, the solution that's being added from your burette is called the titrant, and that indicator changes color when the end point is reached. Now, this is an important vocabulary deal. The equivalence point, like we discussed in an earlier review video of 1341, is when the moles of H plus are equal to the moles of OH minus, and that's the theoretical end of the titration. The practical end of the titration is when the indicator changes color. In a well-designed experiment, the equivalence point and the end point are the same point. In practice, and there's probably a small discrepancy between the two, but it'll be along the order of 1 drop. And so we're usually not too concerned about that difference as long as you've carefully picked your indicator. In addition to using an Erlenmeyer flask and an indicator to see the endpoint of a titration, an alternate setup is to use a beaker and a pH meter. And what you'll do is add a little bit of your titrant and monitor the pH along the way and create what's called a pH titration curve, which is shown in the bottom image. For a strong acid titrated with a strong base, that means that the analyte down here in the beaker is an acid and the titrant in the burette is your base. If you monitor that pH, we're going to start down at a pH of 1, which would indicate that this is a 1 molar strong, or I'm sorry, a 0.1 molar strong acid. And as you add base, the pH very slowly goes up until you get really close to the equivalence point. And then the pH increases dramatically, and then it starts to level off. And once you reach high pHs, where what you're really seeing is just the excess base gradually getting gradually taking over the solution. Now, there are a couple of things to point out on this titration curve. Again, this is a strong acid, something like HCl, reacting with a strong base, something like NaOH, and that's going to make a salt like NaCl plus water. Because it's a strong acid plus a strong base, we're making a neutral salt. So at the equivalence point, you've added just enough base to totally neutralize all the acid. So at the equivalence point, which is point C here, you have no acid, you have no base. All of those have gone to 0, and all you have in that beaker is salt and water. Because NaCl is a neutral salt, the pH will be 7. So if you know it's a strong acid being titrated with a strong base, you don't have to calculate the pH at the equivalence point. It simply will be 7. And there's no equilibrium reaction to consider for extra complications. A common problem that you will be asked to solve with these titrations is to calculate the pH at various points along the way. You might be asked to calculate it at point A on this graph, which is right at the very beginning. Initially, you have only the acid present, so that's actually a pretty easy calculation. pH is minus the log of the H+ ion concentration. Then we've got the region here that's labeled B, which is the region in between the start of the titration and your equivalence point. We've got a couple things going on here. One thing is that the acid is partially neutralized, so some of the acid has been converted into salt, but you also have excess acid present. So for region B here, I guess I should go back and mark these all up. At region A, you have just the acid, and then here in region B, you're going to have still some acid, which is present in excess, and I use the letters X and S to stand for the word excess, like limiting reagent versus excess reagent. We're going to have some excess acid here, plus salt. So the acid that already reacted with the base is being converted to salt, but you have some acid that hasn't reacted yet. When you get to point C, it is all salt, and the pH is 7 for a strong acid, strong base. And then when you get to region D, what you will have is that salt that was generated plus excess base. And so it's that excess base that's really going to dominate the pH calculation. Okay, let's see. One of the things you have to take into account as you're doing this is that as the titrant is added to your analyte, the solutions are diluting each other out. So as you go through and are doing your calculations, you always need to consider the fact that you have added two solutions together, add their volumes to get your final volume, your V2, from the dilution equation. And another thing that you will have to do is use the titration equation to figure out where the equivalence point is before you do any other calculations, because all of these calculations are a little bit different, and we set them up depending on, are you before the equivalence point, at the equivalence point, or after the equivalence point. So you really need to know where you are with respect to the equivalence point before you start doing any math. All right, so here's the example that we're going to work out. We're going to titrate a strong acid with a strong base. We have a 20 milliliter sample of 0.2 molar HBr, strong acid, and it's titrated with 0.2 molar calcium hydroxide, strong base. And let's calculate the pH of the solution after these volumes of base have been added. 7 mils, 9.6 mils, 10 mils, 15 mils. Okay, so we're going to have to do this calculation 4 times, and we're going to illustrate the different regions. I left off of here, what is the pH at 0 mils added base? That would just be minus the log of 0.2, right? Because it would be just pure HBr at that point. One of the things that we do need to take into consideration is that dilution factor. At these 4 points, A, B, C, and D, we're going to have a different dilution since different volumes of base have been added. And of course, we need to figure out where these points are with respect to the equivalence point. So let's use the titration equation and figure out what volume of base will be added to reach the equivalence point. Now, remember that the titration equation, I'm going to write that in up here at the top, that's going to be N sub A, which is the subscript on H in the formula for the acid, times the molarity of the acid times the volume of the acid, is equal to N sub B, which is the subscript on hydroxide in your base, multiplied by the molarity of the base and the volume of the base. Now what we are looking for is what volume of base has to be added in order to reach this equivalence point. And if we rearrange this equation to find that, we've got that the volume of the base will be equal to N sub A times M sub A times V sub A, all divided by N sub B and M sub B. Okay, let me see if we can put some numbers in. I'm going to continue this down below. So the volume of the base added to reach the equivalence point will be N sub A. Well, the formula for the acid is HBr. There's 1 proton, so we'll just use a 1. The molarity of the acid is 0.2, and the volume of the acid used is 20 milliliters. I really should have put molar over here on the 0.2. For the denominator, N sub B, well, calcium hydroxide has a subscript of 2 on the hydroxide, so we've got to stick a 2 in there. And then we're going to need the molarity of the base, which was also 0.2 molar. All right, units of molarity cancel out. The only unit left is milliliters. Let's see, the 0.2s cancel out, and we have 20 milliliters divided by 2, which will give us 10 milliliters. So our equivalence point will be hit at 10 milliliters of added base. Okay. So that is our equivalence point. So that tells us that part C is actually at the equivalence point. Since this is a strong acid reacting with a strong base, it's going to make a neutral salt. And so we don't even have to do a calculation. pH is 7 for part C. For parts A and B, we are before the equivalence point, so we're going to have to figure out the dilution effect from combining the two solutions, and we're going to have to figure out how much of the acid has reacted and how much is left, and use that to figure out pH. For part D, we are past the equivalence point, so all of the acid has been converted to salt, and we have excess base added. It's that excess base that's going to determine the pH. All right, I can see that this is definitely running long, so it looks like we're going to have to split this video into 2 videos.